All right, let's get started. I got your exams graded, okay, so you can give those out at the end of the class and you can see how you did. Okay, so let's get back into NMR spectroscopy. Okay. So remember last time we started hydrogen or proton NMR. Okay. And cover some of the things that we covered in there. We covered the main topic, that of peak position. Remember that? And remember, peak position, what was another name for that? Start with C. The chemical shift. Okay, so this told you where the peak showed up on the spectrum. Okay? And what was the main ingredient we were looking at with the chemical shift?
Hydrogen.
Okay. What kind of thing were we looking for in the molecule? A de-shielder. Okay. Which we saw was typically an electronegative atom, like chlorine or oxygen, fluorine, so on. But we're going to learn more de-shielders later on. So the more closer it was to the de-shielder, the more downfield it was. More downfield or further away from zero, the peak showed up. Okay? So this was the first rule that we learned. We're going to learn two more rules today, okay, to understand this kind of spectroscopy. Okay? The second rule we're going to look at very important rule, that of peak splitting. Peak splitting. Okay? And in peak splitting, the key ingredient is what we call the N+1 rule. The N+1 rule. Okay? I'm going to point to different people here. Okay? See the letter N? Tell me any word, any everyday word that comes to mind when you see the letter N. Okay? What word? Number.
Name.
Name. Neutral. No. Yes or no? All right. Well, none of those N's that you gave me matches what that is. Okay. That N is going to stand for neighbor. Neighbor. Okay. So write it down. This stands for neighbor. Okay? So if I point at you in the blue, who's your neighbor? Which one? Oh, okay. So you got two neighbors. How about you? Do you have any neighbors? You got one neighbor. How about you? Do you have any neighbors?
Not to my mind.
Yeah, you don't have any neighbors there. Okay. So sometimes you could have one neighbor, two, or zero neighbors, so on. Okay? Well, let's apply it to this molecule here. Okay, remember this molecule was our friend, okay? So, let's take a look at our friend. And what we're going to do is draw the NMR spectrum of our friend. Okay. Remember, we labeled these hydrogens A and B. Okay. Which of those two hydrogens showed up more downfield? A or B? A. It was closer to the de-shielder. Okay, so A is here and B is here. Remember last time we didn't draw any peaks, we just put where they showed up. Now let's see what the peaks look like. Okay, so follow me here. Let's make this as simple and painless as possible. Okay, so let's look at A. What kind of peak is going to show up for A? Well, what are the neighboring hydrogens on A? How many do we have? Okay. How many neighboring hydrogens are on A? 3. Why would you say 2? Those are the hydrogens we're looking at. Make this as simple as possible. Okay. So here, for A, N equals what?
3.
Okay, 3. And so 3 plus 1 is 4. Okay. So for A, we're going to see 4 lines for it. This is typically what the lines look like, where the 2 middle lines are bigger than the outer lines. Okay? So we get 4 splits for A. What about B? What's the neighbors for B?
2.
2. And so N plus 1 is what?
3.
3. Okay? So the B signal will be 3 lines, where again the outer 2 lines will be smaller than the middle line. Okay? This is what we mean by peak splitting. Okay? And this is what these peaks would look like. Okay? We call this peak here with 3 lines a triplet, and this peak here with 4 lines a quartet. Okay? So we can have triplets, quartets. We can also have doublets, 2 lines. Singlet, how many do you think that would be? 1 line. And we can have a multiplet. What do you think that is? Okay, a lot of lines. We'll just say more than 4. Okay? We'll see an example of that later. Okay? So this is our friend. If you understand how we did this, then that's going to carry you a long way here. Okay? So let's review here. Since B is giving me a triplet, suppose I didn't know that was the molecule. Since that is a triplet, what does that tell me I have in the molecule? A CH2. See that? Because that's telling me something is next to a CH2, where that CH2 is splitting that signal into 3 lines. And if I ever see a quartet, what does that tell me I have? CH3, where something is next to a CH3 being split into 4 lines. Okay? I'm going to shut the door. Okay? So any questions on our friend here? You understand that friend? Peak position, and peak splitting, I guarantee you that's going to carry you a long way. Okay? All right. Let's do another example. Okay, let's look at this one here. Okay, 2,2-dichloropropane. And let's see if we can get an idea of what this would look like. Okay, so let's draw our spectrum starting at 0. Okay. Here, before we try to answer this, I'm going to give you the third rule. Okay? The third rule is the number of peaks that we get for the molecule. How can I predict if I have 3 or 5 or even just 1 peak? Okay? So let's go ahead and find out. What we're going to do is introduce something called plane of symmetry. Okay, sometimes called a mirror plane. Okay, you probably learned this back in stereochemistry in chapter 5. Okay, let's do a quick review, make sure we know what it is. Okay, so suppose I had a circle here. Is there a plane of symmetry in that circle?
Yes.
Okay, there's a lot of them, aren't there? I'll just draw one right there. So the plane of symmetry designates that one side of that plane is the same as the other side. Okay? So with a circle, that is the most symmetrical object, isn't it? Because you can draw tons of mirror planes for it. Okay? Does your body have a mirror plane? Yes, right down the middle, and so on. Okay? Well, let's come to our molecule here. Does that molecule have a mirror plane?
Yes.
Okay, right down the middle. Okay, so what can you say about those two CH3s?
Mirror image.
Okay, so yeah, so let me give you some help. If the two hydrogens are related by a mirror plane, write it down, they are equal or the same. They are equivalent. Okay? So those two CH3s are the same, right? So how many signals will this one give you? Can you get it? How many signals? One, because I just have one hydrogen type, don't I? So I got here and here, since they're the same, I'll just give them the same letter, A and A. Okay? So make sure you have it down. If I have hydrogens related by the mirror plane, those are the same. Okay? So here, how many peaks would I get? One. Now, what would the peak look like? Doublet, triplet?
Quartet.
What's it going to look like?
A quartet.
No. What's the peak going to look like? Use the n+1 rule. It's a singlet. Okay? What's the neighbor here? Are there any hydrogens here? No. So n is 0, like where you are. Okay? So 0 plus 1 is 1. So I would get a singlet. I'll just draw it there. Okay, there's nothing to compare it to, so I'll just draw one line. Okay, how many hydrogens would that signal represent? 6 hydrogens, very good. Okay, because how many are with A? 3 and 3 for a total of 6. Okay. And this value here of the number of hydrogens for that signal is what's called the integration of that signal. Okay? So anytime you hear the integral value or the integration of a signal, it's always asking for the number of hydrogens corresponding to that signal. Okay? And we'll see in live NMRs, sometimes they'll draw this curved line that looks like an integral sign, remember in calculus, over the line. That's basically representing, measuring the area for that curve, and the area corresponds to the number of hydrogens for that signal, okay? And it's very nice. The NMR machine can do that for you at the click of a button. And you can see that's valuable information. You see what valuable information we're getting? We're getting what kind of signal it looks like. So if this is a single line, that means that hydrogen is next to a carbon with 0 hydrogens. Valuable information. I'm getting how many hydrogens are per that signal. Wow, valuable information. Okay, so you can see how this is more powerful than IR, isn't it? Okay, and we'll do some more examples to show that as well. Okay. Any questions on this example here? Okay. I'll just get them later. Thank you, though. Okay. Before we proceed any more here, let me draw this molecule. Okay. If you look at that molecule, are there any mirror planes in that one? Yeah. So here and here. How many signals do you think you would see for that? Just one. Okay, so they're all equivalent. Okay. Would I see any splitting?
No.
No. So I'd see what? A singlet representing 12 hydrogens. Okay? Well, this molecule is what's called tetramethylsilane. Okay? Or oftentimes abbreviated TMS. Okay? And what we do with TMS is, if you look, on the periodic table, carbon is a little more electronegative than the silicon. So the silicon donates electrons to shield those hydrogens. So these hydrogens are very, very shielded. Okay? And what we do is we mix TMS with the sample molecule that we want to look at. We just put a tiny little drop of TMS. And TMS is going to give us a singlet. What? Very far where? Upfield, right? Because it's very shielded. Okay? And what we do is we're going to assign that a value of 0. So in all the NMRs that we'll see, we're going to see a tiny little singlet at 0, and we know what it is, and we can just forget about it. Because what it does is it serves as a reference so that we assign that to 0, so all the other peaks are going to be where? Downfield from that. So all the chemical shift values will be dependent on TMS that we assign 0, and so everything else will have a value greater than 0. Okay? So that's all we use TMS for. And you'll see that when I hand out some live examples to you. Okay? All right, let's come back and look at another molecule. Let's suppose I gave you cyclohexane. Could you predict what the NMR would look like for that? Any ideas?
Would it be a singlet with 12
Okay,
hydrogens?
single peak.
With 12 hydrogens?
Is it going to be a doublet, triplet?
No.
Singlet?
A singlet.
Okay. So remember, on all these carbons, I got 2 hydrogens. Okay, so won't that split those into a triplet? That's what N is, isn't it? Won't that give me a triplet?
No.
Okay. No, it won't. It won't. Here you want to write down something new. Hydrogens that are the same will not split each other. Hydrogens that are the same will not split each other. Now these are all the same. You got all these mirror planes here. Okay? Since they're all the same, I'm not going to get any splitting. See that? So I'll see a singlet. In fact, it's going to be what? A giant singlet representing what? 12 hydrogens. Okay? Okay, it'll be pretty close to 0 as there's no de-shielders on there. Okay? So it'll be pretty far upfield. Okay, so we will see there's a correlation with the size of the peak. The taller that peak is, the more area, it's saying I have a lot of hydrogens with it. Okay, a very tiny peak means I have very few hydrogens. Okay. What can we say about the symmetry of a molecule? You can help me here. Fill in the blank. The more symmetrical the molecule is, what will happen to the number of signals? Do I get more signals or fewer signals? Fewer signals. Okay, and you see that here with cyclohexane. And that makes interpretation easier. It gets harder, what? When I have a lot of signals, that tells me I don't have much symmetry, and that tells me I got a lot of work ahead. Okay? We don't like that. but sometimes we have to face it. Okay, let's do another molecule here. Cyclohexanone. Why don't you take a couple of minutes and see if you can figure out what the NMR looks like for this. You may want to draw the hydrogens on there, start labeling them, and then draw the NMR. Okay, I think you can handle this. I'll give you some help by drawing the graph here. You got a pocket. We have 3 rules. What do you think the first rule you always want to use is? What's the first thing you always want to figure out? The number of signals using the mirror plane. Okay? So always figure out the number of signals first. Then that will help you to label your hydrogen types. Okay. How many signals is this thing going to give? How many signals, Puckett? It's not 2.
One. Is this the N plus 1 rule?
What are you using in number 1? What tool are we using in number 1? The plane of symmetry. Does the molecule have a plane of symmetry? No. It's got a nice juicy one. Where is it? Right down the middle. Okay? If you can't figure that out, you're done. Just write on the paper, give me a 0. Okay. So how many hydrogen types are there? I already said it's not 2.
One.
Okay? Did I teach you guys anything this morning? I thought I just taught you something. How many hydrogen types?
thought one, but I'm not sure.
Quimby, can you help us? What's your shot?
There's only, those are CH2s, right?
Yeah.
So that's one.
Got two at each card. Okay? So these two are the same. These two are the same. And then you got the C's down here. How many we got? Three. That wasn't that hard. First class got that one right. Any questions on how we got three? Okay? So even though the mirror plane contains these two hydrogens here, they're still counted. And they're different because they're not reflected up here. So that's reflected there, that there. Okay? That's the first thing you always got to do. What do you think the second rule we're going to use? Okay, at a peak position. What are we going to ask here?
Upfield or downfield?
Upfield, downfield. Which peak is going to be most upfield? A, B, or C?
C.
C. Why C? The most upfield. She said C. Tell me why C. You were right. I'm asking her.
Because O will be considered the deshielder and it's pooling.
What's the deshielder?
Oxygen.
So it's what from the deshielder?
Furthest from the deshielder.
Furthest away from the deshielder. So it'd be most upfield. Okay? So C, then what? B, and then what? A. So there's my peak positions. What's the third rule we're going to use?
Peaks.
Splitting. Okay? So I got to tell you what the peaks look like. Okay? What is A going to look like? You got four choices. Give me a choice.
It's one, right? 'Cause you don't count the ones that they're identical to.
Just give me your answer.
One.
Singlet, doublet, triplet, quintlet. Wrong. I hear triplets. Very good. Why triplet? A is next to what?
B.
B, that has two hydrogens.
Plus one.
So 2 plus 1 is 3. Okay? So A will give me a nice triplet. Okay? Let's come down to C. A little harder one, but I think you can handle it. Okay, let's get the front row, the harder one here. What is C going to look like? Singlet, doublet, triplet, or quartet? Wrong. It's going to be what, A?
Triplet.
A triplet. Why a triplet? It's next to B. B's are the same, remember? So it's only going to be split by one of the B's. Okay? So C, triplet. Now what's B going to be?
Multiplet.
Now you're multiplet. Okay? So I'm between two different ones, so a triplet and a triplet. So I got lots of lines there. Okay? So I'll just draw it like this. Yeah, something like that. Just draw more than 4 lines. We'll get the picture. Okay? So B would be there. Any questions on that? Yeah.
So when it's multiple ones, as long as we draw out more than 4, we don't have to know the exact
That's
number?
right.
Okay.
Yeah, that's sufficient. Any other questions? Yeah,
But what were you saying earlier, that the hydrogens are the same will not split each other?
right, hydrogens that are the same don't split each other.
What
Okay,
do
so
you
back
mean
to
by-
the cyclohexane.
Okay.
Yeah. You got it, Quimby?
Now, with the hydrogen types, like, what are you looking for?
You're looking for number of signals due to the mirror plane. Then labeling them. Okay. All right, let's do one more. Let me give you this handout here. Let's look at a live one. Okay. Pass these on this side. Grab that one. Tell me if you need any more. They're coming.
They're coming from that way.
Okay. All right, just hold on to it. Okay, so let's take a look at the top one here. Okay? See how you see a signal at 0? Okay, you should be looking at your paper. What's that due to?
TMS.
TMS, so everything is more downfield than there. Okay? And then you see the molecular formula in the top left-hand corner. That's what you would see on the exam. I'll give you the molecular formula. I'll give you the NMR. You draw the molecule. Okay? So let's see if we can start figuring this out. Okay? I gave you the molecule 1-chloropropane. I won't do that on the exam. Okay? Not that nice. Okay? But here, let's go through our questions. First question, tell me an answer. How many signals?
3.
3 signals. So how many hydrogen types? 3 hydrogen types. Okay? So, I might want to write that down so I keep information in front of me. Remember, you're playing the role of an investigator. Keep all your evidence in front of you so you work with it. Don't try to keep it in your mind. When you look at things, it's easier to work with. Okay? Like making a grocery list before going to the store. That way you don't forget. Okay? So, second question, we can see the peak positions. That doesn't really help us much here. Third question, the splitting. Okay, what does A look like?
Triplet.
A triplet. What does C look like? A triplet. What does B look like? A multiplet. Okay. So you can write that down if you like. And then we try to get to work here. Okay. So if I see a triplet, what does that tell me I have in the molecule?
CH2.
A CH2. And how many of them do I have? I got 2 sets. Okay. Is there any way I know that there's a CH3 in here? I'd have to see a quartet, wouldn't I? I don't see a quartet, do I? Okay. But, okay, I do know I have things that are next to CH2s. So a CH3 could be next to a CH2 being split into a triplet. Okay? So that's what I have here with 1-chloropropane. See if you can label the hydrogens there. Okay, I labeled the peaks for you. Match the peak letter with the hydrogen in the molecule. Okay, which letter will be C? Closer to the de-shielder. B,
CH2.
okay, see why that's a multiplet? It's between that and that, two different sets of hydrogens. Okay, so I'm getting tons of splitting, multiplet. Then lastly, this is next to that furthest from the de-shielder. So that would be A. Okay? Question?
Yes. Okay, you know how we just identified if there was a CH2? We couldn't like assume that there was a CH3 because B was a multiple.
Not really, because there could be other things next to it.
Okay.
Okay, so you have to be careful about assuming too much.
Okay.
But if I showed a quartet, then I could write it down.
Okay.
Okay? Other than that, we got to start working a little bit more. Okay? So everything's not so obvious that it's given in the problem. Okay? So I just wanted to introduce you to this. Okay? Make sure you know the 3 rules. We'll do more examples on Monday. Introduce you to a live example. Okay? Now, let me give you back your exams.